In the previous lecture, we have discussed complete metric spaces. And it's not a surprise that completeness is a good property. And today, we will see what can we do in complete metric spaces and what are they good for. But before we go to the main result of today's lecture, we will need some preparation. We will briefly speak about the continuous mappings, then introduce one specific type of a continuous mapping, and then we will go to the main theorem. So this definition will not be a surprise for you. So if we have a mapping between two metric spaces, x1 row 1 and x2 row 2 be metric spaces, mapping phi from x1 to x2 is said to be continuous if for every continuous at a point x0 from x, if so mapping is continuous at a point if for every epsilon greater than 0 there exists delta greater than 0 such that for every x from x such that the distance rho 1 between x and x0 is less than delta, we have that the distance between phi of x and phi of x0 is less than epsilon, and this is the distance in x2. Well, pretty standard definition. So you have seen this kind of definition before in calculus. The only difference here is that we replaced the absolute values between two elements by metric. But the idea is the same. If two elements are close to each other, 2 points are close to each other, then the values of the function should be close to each other as well. Well, there is an equivalent definition in terms of sequences. So let me briefly state the result, and I will leave it for you as an exercise. A mapping is continuous at x0 if and only if for every sequence converging to x0, the values of the function phi xn converging to phi of x0. Well, we have defined the function continuous at a point. We will call a function continuous if it is continuous at every single point. Well, in this theorem we have restated, we gave a criterion for the continuity of a mapping. We will consider one more criteria for the continuity, but for a special type of mapping the mapping which are onto the whole set. In other words, surjective mappings. So let us first note that if a mapping is surjective, if a mapping is surjective, which means that phi of x1 equals to x2, so it's onto the whole space, then the inverse image of any set from x2 is non-empty. That is, what do I mean by inverse image? It is denoted as phi inverse m, which consists of all points from x1 such that phi of x belongs to m. So this is the definition of inverse image. Let me put two more dots here to say that it's by definition. So by writing phi inverse, I do not mean that the function, the mapping phi, is invertible. So it may not be invertible. And now I will state a criteria for the continuity of a mapping in terms of the inverse images. Theorem. A mapping is continuous if and only if the inverse image of any closed set is closed. And most probably you want to ask me, why on earth do I need the inverse images? Why don't I use the usual images? So the point is that for the usual, for images, not the inverse images, for images, this result is not true. Example. In this example, we consider an identity mapping from the interval 0, 1 to a set A, where A is a circle of length 1. So we have an interval and a circle. And a circle. So if we choose, for instance, a point here, call it phi of 0, so just initial point. So what phi does, pretty much, it takes the interval and makes a circle out of it. Actually, to make this mapping 1 to 1, I exclude 1 from the interval to make this mapping 1 to 1. Because if I include it, then this point phi of 0 equals to phi of 1, so 2 points are mapped to the same one. Now, let's take D to be the interval 1/2, 1. This interval, if we consider this as a subset of a metric space, then this interval is closed. In the metric space 0, 1 with the usual metric on the real line. But the image of this set, so this will be phi of 1/2, and if it goes this way, then that will be the image. And this image does not include this point, this designated point. But the image phi of D is not closed. First, let phi be continuous. And let M from X2 be closed. Set, let it be M2. Let it be M2 and set M1 to be the inverse image of M2. We want to show that M1 is closed. So let's take X from the closure of the set M1. Let's take X from the closure of M1. There exists a sequence Xn of elements from M1. There exists a sequence such that it converges to X. Since our function is continuous, then phi of Xn converges to phi of X, well, in X2 of course. By the construction of the inverse image, we conclude that phi of Xn belongs to M2, and the set M2 is closed. We conclude that phi of X belongs to M2, which is by definition of the inverse image implies that x belongs to M1, and so M is closed. M1 is closed. So we've taken a point from the closure and proved that it belongs to a set, which means that this set is closed. So let phi inverse of M is closed for every closed set M in X2. We want to show that phi is continuous. Let us take a point X from X1 and let Y, being phi of X, to be the corresponding point from X2. And also, let us take epsilon greater than 0 and consider a ball around Y of the radius epsilon. Well, this is an open ball, which means that its complement is closed. Hence, the inverse image of this set is closed as well. Since the function phi, the mapping phi, is surjective, we can write this inverse image of the set difference as a set difference of inverse images. Two fairly simple observations. Since this set is closed, this set is open. And moreover, by the definition of the inverse image, X belongs to this set. So we've taken X, considered its image, considered a ball around this Y, and take the inverse image, so X belongs there. Let me do some drawing, maybe it will be helpful. So let this one be X1, and this one be X2. So we considered X here, took it to some Y, and then we considered a ball of radius epsilon around Y. And then we consider the inverse image of this ball. So what we know about this set, that it contains X and it is open. X, a point, belongs to an open set, means that this point belongs to this set together with some ball. There exists delta greater than 0 such that the whole ball around X and of the radius delta belongs to this inverse image. And what is left now to write down the definition of continuity, because we have proven it in fact. So what we've done, for every epsilon greater than 0, there exists delta greater than 0, such that for every X in X1, such that the distance between X and X1 less than delta, which means that let's go for X1. Which means that this x1 belongs to this ball, so the distance between x and x1 less than delta, so it belongs to this ball. Hence, the image of this ball belongs to this ball around y, which means that phi of x minus phi of x1, which is y minus phi of x1 less than epsilon, which means by definition that phi is continuous. After having this preparation and discussion about the continuous functions, continuous mappings, we will go to the main topic of today's lecture, which is named the fixed point principle. For this fixed point principle, we will not only consider the continuous mappings, but we rather need some special type of continuous mapping, which are termed contractions. From a metric space X into itself is said to be contraction. If there exists a constant C such that the distance between AX and AY less than or equal to this constant times the distance between X and Y for any X and Y from X. Well, it is easy to see from this definition that any contraction is a continuous mapping. Yes, of course. Yes. Less than or equal to 1 or strictly less than 1.
A should be.
Oh, okay. Yeah, I will go for A over here.
Okay.
Sorry about this. Let me now state the main theorem, which is the fixed point principle itself. So if we take a contraction, on a complete metric space, for any contraction, on a complete metric space, space X, there exists a unique fixed point by fixed point, I mean that AX equals to X. So we take any complete metric space, any contraction, and it has a unique fixed point. And moreover, this point can be approximated by a successive application of our mapping A to any point. So it's not just the existence of this fixed point. The second statement tells us that we can take any point from our metric space and then successively apply the mapping A to this point, and we will get closer and closer and closer to the fixed point. and it holds for any starting point. So let A be a contraction on a complete metric space, and let x naught be some point from x. And we consider this sequence of consecutive application of our mapping A to a function x naught. x1 to be ax naught, x2 to be a x1 or a squared x naught, and so on. xn to be a to the power of n of x naught, and so on. I will show that this sequence is a Cauchy sequence. Let us take m and n large enough and let us consider the distance between x m and xn, which is by definition of the sequence a to the power of m x naught, a to the power of n x naught. I will write this as a to the power of n of a, another way around, m minus n a n x naught. This is for the first term, and the second term I will keep it as it is. A is a contraction, which means by definition that this is less than the distance between, I wrote it initially, that was right, a n here and m minus n here. Well, it doesn't matter in which order, but anyway, I will write it like this. So the distance between these 2 points times constant to the power of n. So this is just what we have over here, the same operator. A is a contraction, a to the power of n is a contraction as well, with constant for some constant c, which is less than 1. Let me now go back to the sequence x m minus n. That's what we have here. And now I will use the triangle inequality to add plenty of terms. So this is less than or equal to c to the power of m rho x m minus n x m minus n minus 1 plus rho x m minus n minus 1 m minus n minus 2 plus so on up to rho of x2 x1 x1 x0. And now each term in this sum can be written in this form. And now I will estimate each of these terms to get to rho of x1 x naught multiplied by some constant. So I use the fact that A is contraction. We have c to the power of n, distance between x1 x naught. So over here we have a part of the geometric series. It's 1, c squared, and so on. There are finitely many terms. Let's make them infinitely many. So estimate from above. C to the power of k from 0 to infinity. But c is less than 1, so this series converges. So it equals to rho x1 x naught c to the power of n1 minus c, which tends to 0 when n tends to infinity. So we've chosen arbitrary, well, large enough but arbitrary m and n, and proved that the distance between xm and xn tends to 0, which means that the sequence xn is Cauchy sequence. But our metric space is complete, so this sequence converges. But we know that our mapping A is contraction, and thus it is continuous. So let's use the continuity. We have A of x equals to A of limit of xn n tends to infinity equals to limit A of xn. But by definition of the sequence xn, A of xn is nothing but xn plus 1. That's how we define it. But the sequence xn is still convergent. If we shift it by one element, it still converges to the same element. So x is, in fact, a fixed point. But in the statement of the theorem, we claim not just the existence, we also claim the uniqueness. So let's prove that the fixed point is unique. So let there exist 2 points such that A of x is x and A of y is y. So we suppose that there are 2 fixed points. Then the distance between x and y equals to the distance between ax and ay, since they are fixed points. But A is a contraction, so it is less than or equal to c times the distance between x and y for some c strictly less than 1, which implies that this number is 0. And x equals y by the axiom of metric. Hence, the fixed point is unique. Let us now discuss some applications of the fixed point principle. As a first application of the fixed point principle, let us consider the equations on the real line. Let f be a continuous function on the interval 0, on the interval AB, or rather, for a continuous function f, consider an equation. So we want to solve this equation. So we are interested in whether there are solutions and how many solutions are there. So let us additionally suppose that f is a Lipschitz function. And also suppose that f of AB belongs to AB. So the function maps the interval AB into itself. All these assumptions are needed to apply the fixed point principle. So the fact that the function is Lipschitz tells us that as a mapping, it is a contraction, and this fact tells us that the function map acts on the same metric space AB with the usual metric. And so by the fixed point principle, this function f has a unique fixed point. So you probably use this principle to find the roots of some polynomials, so zeros of function. So if we have if we want to solve an equation, say g of x equals to 0, then we can consider f of x equals to g of x minus x, and if f is contraction, is, say, Lipschitz, then there exists unique x in, well, in some interval, unique x, such that f of x equals to x. But this is, well, equivalent to the fact that g of x is 0. That's how we use the fixed point principle in on the real line in dimension 1. It can be equally well used in dimension n. So example 2. So let us consider Rn with some p metric. And also let us, the equation ax equals to x, where A is n by n matrix and x is n-dimensional vector. So this equation has a unique solution if A is a contraction. I will leave it for you. I leave it for you as an exercise. Though, be careful about the condition for A being a contraction, because this condition will depend on the metric. For different metrics, it will be different forms condition. So we have applied fixed point principle in the dimension 1, in the dimension n, any arbitrary but finite dimensional space. The most interesting stuff happens when we apply the fixed point principle in infinite dimensional spaces. Let us consider the Fredholm integral equation, which stated as f of x equals to an integral from x0 to x1, k of xy, f of y, dx plus g of x. K is generally termed a kernel. The kernel K of two variables is a continuous function. on, let's simply go for A and B. That will be simple. A and B as a limit of the integral, and I will also plug a constant lambda in front of the integral to make it even more general. Well, to make it even more general and the fixed point principle more applicable. So we want kernel to be a continuous function on AB times AB, and we want G to be a continuous function as well. So, and then we can look for a solution in the class of continuous functions. And G also a continuous function on AB. F is the function we want to find, the unknown function, and lambda is some numerical parameter. So let us try to apply the fixed point principle to this equation. So let us consider a mapping A from continuous functions on AB to itself, AF of x equals to lambda from A to B, kxy f of y dy plus g of x. According to our assumptions, the right-hand side is a continuous function, so our mapping A in fact maps continuous functions into continuous functions. So the next step is to show that A is a contraction. So we consider this set of continuous functions as a metric space, but I forgot to specify the metric. Let's take the uniform metric. Let's check whether A is contraction. The metric between A F1 and A F2. It is. So just plug in the formula for A. Now let's make the estimates G cancel each other. These G and these G cancel. So, and we are on AB. So it is less than or equal to the function k, the kernel k. We suppose that it is a continuous function on AB times AB. So continuous function on a compact set, so it attains its maximum. Less than some m, and this is nothing but the distance between F1 and F2. I forgot to multiply by the length of the interval, so we need to multiply by AB as well over here. B minus A. So over here we need to multiply by B minus A as well, and the same story here. For lambda less than 1 over m b minus a, our mapping is a contraction, which means that the Fredholm equation we started with has a unique solution in the class of continuous functions over the interval a. Fredholm equation has a unique solution. In our assumptions, we assumed quite a lot. We assumed that the kernel is continuous, and this term, the function g, is continuous as well. These are quite strong assumptions. But under these assumptions, we're in a very nice situation. The equation has a unique solution.